Hey guys, in this lecture I'm just going to go through Energy Skate Park and I'm going to talk about it so hopefully we're all on the same page and we're all getting the same things out of it. So again, what is the purpose of Energy Skate Park? Mostly the point is to show you how the conservation of energy works. So let's start with this simple track. We're going to drag it to the bottom just because we want the potential energy to be zero when it gets to the bottom of the track. And we're going to take our skater, we're going to place him somewhere up here at the top of the track. And we are going to, let's look at a couple different graphs. Let's look at the pie chart first. So we're going to say show pie chart. And so if you look at this right now, this entire pie chart is blue, meaning blue is potential energy. All of the skater's energy right now is potential energy because he is stopped. As he goes back and forth on this ramp, each time he's going to reach the same exact height on the opposite side as he starts at. And the reason is because right now on this track there is no friction. There's no friction, so the skater will not slow down. In fact, this skater will reach the same exact height every time and will go forever as long as there's no friction on the track. You can see that all of the skater's energy at the top is blue, meaning it is potential energy. All of the skater's energy at the bottom is green. So let's step through this a little bit more slowly. Again, we start at the top, it's all potential. The farther we go down, the more kinetic energy we get, until at the halfway point, we're actually at half potential and half kinetic. As we get 3/4 of the way down, it's about 75% kinetic energy. And when we get all the way down, it is all kinetic energy. And then it starts going back up. As the skater's kinetic energy increases, his speed increases. So as the skater goes down and gains more and more kinetic energy, you'll see that with each click he actually covers a larger distance. He's going faster and faster and faster as he goes down. If the potential energy is getting bigger, that means he's losing kinetic energy because it's being converted to potential, and he will go slower and slower and slower as the blue pieces of pie gets bigger and bigger and bigger until when it's all blue, we have nothing but potential energy and he's stopped. Okay, let's look at that in a bar graph. It basically shows us the same thing. You can see the kinetic energy gets the highest when he reaches this midway point. Right now it's all potential energy. It's showing a little bit of thermal energy, but basically it's all potential energy. Potential energy gets smaller and smaller and smaller. Kinetic energy gets bigger and bigger and bigger. They reach the bottom when it's all kinetic energy. And then finally, this is my favorite one, the energy versus time graph. We're going to delete some of this other stuff here real quick. Okay, so as we push play here, you can watch when the blue line, the potential energy, comes to a peak, he's at the top of the ramp. When the blue energy drops to zero, he's at the bottom of the ramp. When he is at the top of the ramp, his kinetic energy is zero. He's stopped. When he's at the bottom of the ramp, he's going his fastest speed, and so his kinetic energy is a max. So these peaks should always exactly offset each other. And remember, the track we're looking at right now is a frictionless track, so these peaks don't get any smaller over time. They actually reach the same height each time. Now, if this was a more real-world situation, what would this graph look like? Let's turn on the friction. Oops. So, track friction, I'm going to put it on a fairly small amount. watch this simulation again. Now, over time, the total amount of energy, by the way, up here in yellow, is still staying the same. That's showing you that energy is actually never created or destroyed. It's just transformed into different types. So the amount of potential and kinetic energy is going down over time. We still have the most kinetic energy when he's at the bottom of the track, and the most potential energy when he's at the top of the track. So as this skater approaches the bottom, we're going to get more and more kinetic until we reach a peak right there. And then as we start going up the track, we get more and more potential energy until he reaches the top of his motion, and that's a maximum potential energy. And somewhere in between, where these two lines cross, we have a half kinetic energy and half potential energy. But now what's happening is this skater keeps moving. Friction continues to slow this skater down, which means where is that energy going? If this skater is slowly coming to a stop, energy can't be created or destroyed, so where is it going? Well, it's being lost as heat. So when things rub together, just like when you rub your hands together, friction generates heat, which is a different form of kinetic energy. The molecules in the wheels of the skateboard and the track and the air around the skater are all going to start heating up and moving faster. So that energy is not gone, it's simply transformed into heat, kinetic energy. So you see up here that when we're at start, all of it's potential energy. And when we finish, there's no potential energy, no kinetic energy, and all of that energy is radiated off to space as heat energy. But the total amount of energy in yellow still stays the same. All right, a couple more things. What would change about this pie if I were to get a different skater? Well, I'm going to turn the friction off really quick. And we're going to choose a different skater. We're going to choose a bulldog. Okay? What actually changed has nothing to do with the amount of blue or the amount of green in the pie chart, but the size of the pie chart has changed. That means there's less total energy with the bulldog skater than there was with the boy skater. Why? Because the boy was heavier. So again, I'm going to go back to the boy here really quick. The pie gets bigger. If I go all the way down to the ball, the amount of energy is pretty small. And if I hit the bug, now my energy is really small. So the more mass we have, the more total energy there is at any given point. All right, let's look at that with a bar graph. Okay, so you can see my total energy here. It's still going back and forth between potential and kinetic, but as I get a smaller and smaller skater, my total energy here will get smaller and smaller and smaller. Less energy, even less energy, and even less energy. Okay, and the last thing you can change on this simulation is the gravity. So I can go to the moon. And I'm going to return skater. And what happens is the bug now is actually going slower. Why is the bug going slower than before? Well, because there's less gravity, therefore the original gravitational potential energy was less, and then his kinetic energy will actually be less at the bottom. If I choose this skater again, what's different? Again, we have a smaller total pie. We have less total energy because of the smaller gravitational force, but the percentages are still the same. It's still completely potential up here and completely kinetic down here. So again, 100% kinetic energy doesn't mean he's going fast, it doesn't mean he's going slow, it just means that all of his energy is currently kinetic energy. If I go to Jupiter, where there's a much stronger gravitational field, then what will happen to this skater? And if you think about it, what's going to happen? He's going to have more total energy because there's more gravity and because Jupiter is actually larger than the Earth, has more mass than the Earth, and he will be going faster. So now there's more total energy. You see this bar is really tall here, and the skater goes a lot faster. Okay, so what do we take away finally from this energy skate park? First of all, energy can never be created or destroyed, only transferred. So this yellow total energy bar, no matter what simulation you do, friction on or friction off, always stays the same. Energy is converted, so you can convert it from total potential energy at the top to completely kinetic energy at the bottom. Last of all, what happens in the real world when we have friction? Slowly, over time, the kinetic energy and potential energy will decrease. And we're used to seeing this. When you roll a ball, it eventually comes to a stop. A skater on a ramp will eventually come to a stop. But that energy isn't gone. It's simply transferred into heat energy, which is the motion of molecules in the air and the ramp and other surfaces that eventually can radiate off into space. All right, that's it for this lecture. We'll see you guys next time.